Let's go ahead and get started, if we may. Yes, question? I'm sorry? I don't know. I'll let you know. I need to coordinate with the GSI and the reader. So it's not due for another week, right? So, okay. We'll let you know how to turn it in. I guess I'm assuming that everyone is settled on a lab session. Okay, if not, you need to contact Di or Kevin and figure out how to solve whatever lab problem you've got. Okay. I see some stunned faces. There is a lab associated with this class, right? You know that. I think that one lab met yesterday, right? There was some confusion about the account forms having been missing, but I think they eventually turned up, I hope. All right, any questions about logistics or content? Yes? What is the discussion section? Well, formally there is no discussion section with this class, but we were thinking about organizing an informal one, which would just be kind of an extra resource for asking questions, delving into the material in a little more depth and that kind of thing. Certainly not required. But I think we have the luxury of having a little bit of extra GSI bandwidth, and so we're trying to find ways to make it useful to you guys. Yes? Is there a way to change the time of the discussion section? Sorry? So what is the current status? I actually am not sure what. Thursday from 1 to 2? And yeah, I guess having a fixed time like that with a group this big is a problem. Let me talk to the GSIs. Maybe we can schedule 2. But one thing that would be helpful is if you send email to the GSIs and CC me, indicating what times you're available. So if you have a conflict with the GSI, the scheduled discussion section, send email to us, okay, and indicate when you're available, right? And then we'll try to work something out. So they scheduled it for Wednesday 1 to 2. Is that right? Or Thursday. So it seems like we should realign the problem sets maybe so that they're due on Fridays rather than on Tuesdays. Because, sorry? You like Tuesdays better? Yeah. Maybe we can get them to put the other discussion section on Monday. Let me talk to them about that. It has to also not conflict with the lab time, obviously. All right, I just wanted to point out a logistical issue. If you go to the website now, the screen capture for this course is available with some time delay. It's a little bit annoying to watch. I find, it's, I'm not a trained actor. My speaking skill when it's devoid of an image is not exactly, it probably drive you nuts to, use that too heavily, but it's a resource. If you need to go back and review something, maybe it'll be useful. The tablet capture doesn't actually happen in real time. It gets sampled at, I think, maybe 2 frames a second or something like that, and there's quite a lag, so it's not quite the same experience, but hopefully it's better than nothing. Okay, so I want to remind you of where we were, okay? We were using F equals MA as a basis for modeling physical dynamics, okay? And the way that translated into a model of a system is shown on this slide here, which kind of summarizes the model that we constructed the last time of a helicopter that is looking at a particular aspect of the helicopter, which is how the tail rotor keeps the body of the helicopter from spinning around, rotating when the friction from the main rotor causes a torque on the body of the helicopter, right? And so we came up with this rather simplistic controller. And the idea here is that the F equals ma translates into this integral equation, which says that the angular velocity is equal to the initial angular velocity plus a scaled integral of the net force, the net torque on this helicopter. Okay, and we constructed two rather distinct kinds of models the last time. The first was simply the differential equation, or equivalently the integral equation if you integrate both sides. The integral equation has the advantage that it directly represents your initial conditions. And then the second type of model that we constructed is this one that we call an actor model, where you break down the system into components that have as inputs and outputs signals that are functions. So the helicopter itself here is represented as a subsystem that has as input a torque that is a function of time. And its output is an angular velocity, okay, which is also a function of time. So you can think of the helicopter box here is a function, and the domain of this function is a set of functions, the set of all possible torques as a function of time. And the range of the function is the set of all possible angular velocities as a function of time, okay? So it's a little more, you got to get your head around this issue that the domain and range of functions need not be numbers. They can be, you have endless possibilities for how to define the domain and range of functions, and the domain and range can themselves be sets of functions. And once you allow for that, it's pretty easy to interpret these sorts of block diagrams as simply compositions of functions. Because the controller here, for example, which has as input also a function of time, a measurement of the error. Okay, so the way that this works is if you want the helicopter to not rotate, you input a constant signal, right, which is simply, it's a function of time, but it says, I want the angular velocity to be 0 at all time. Okay? That's a desired signal. You would like the helicopter to not rotate. Okay, that's what you're saying. You compare your desired signal against your measurement of what the helicopter is actually doing. Okay, and you come up with an error signal. You scale that error signal. So this particular system, subsystem here, simply takes the current value of the input at any time, scales it by a constant k, and produces an output that is the scaled version of that input. Okay, so there's a scaled error. That scaled error you interpret as a torque, okay, which is, the way you realize this thing, of course, is you take this error signal and you use it to drive the motor that's driving the tail rotor, right? If the error is large, the motor goes faster. If the error is small, the motor goes slower, okay? And so that measured error translates into a torque, and when this thing settles into steady state, ideally, the error will be 0. In fact, this controller is kind of simplistic. If you've taken a control systems class like EECS 128, or a mechanical engineering equivalent to that, which I don't know what the number is, then you would recognize this as a proportional controller, and you will realize that, in fact, the proportional controller can't actually, in general, drive the error to 0. It's always going to have a steady state error, okay? But this isn't a control systems class, so we're going to pretend this is a good enough controller and march ahead, okay? So as an exercise, if you have taken a control systems class, you might, just as an exercise, see what happens when you improve this controller, okay? But the point of this class isn't the design of the controller. The point is the style of modeling. The fact that we're using differential equations to describe the dynamics of a physical system, the fact that we're able to take these differential equations and tease them apart into subsystems, and then compose these subsystems together to build bigger systems. Okay, that's really the point that we're trying to get across. Now, an interesting question here is how would you measure the angular velocity, right? So one of the things that's required in this controller is you've got to be able to compare a measurement of what the helicopter tail is actually doing against what you would like it to be doing. How do you measure angular velocity? Gyroscope. That's a pretty darn good way to do it, okay? So a gyroscope traditionally is a mechanical device, right? You have a flywheel that's spinning, and what happens is you mount it on a gimbal such that it is kind of free to rotate in arbitrary directions, right? And what it'll tend to do, just because of Newton's first law, right, which is that things in motion try to stay in motion going in the same direction that they're going in, is that as your vehicle rotates, the gyroscope will remain stable, okay? And so you can measure the position of this spinning disk with respect to the position of the vehicle, right? And so what will happen is that as the tail rotates around, if you have a spinning disk that is vertical, right, the spinning disk will remain vertical as the tail rotates. You can measure that angle between the tail and the spinning disk, and you can tell that the tail has rotated, okay? These days, gyroscopes are built often with optical techniques, so a ring of an optical signal, for example. There's a number of techniques, but they can be integrated onto integrated circuits made quite small, and they're a pretty good measure of rotation. Okay, you could also use an accelerometer, like what is in the iPhone. Okay, but an accelerometer is not quite as good as a gyroscope for measuring angular movement, okay? And the reason is that an accelerometer measures also the gravitational force, and consequently it's sensitive to tilt. In fact, it's a very good way of measuring the tilt of an object with respect to a gravitational field. Okay, that's primarily how it gets used in the iPhone. It doesn't get used so much to measure movement. It gets used to measure tilt. Okay. All right, so we're gonna talk a bit about sensors, because one of the things in designing cyber-physical systems, having an understanding of what your sensors are actually measuring, how they work, what are the weaknesses, what are the problems that a sensor can give you, that's essential, because cyber-physical systems require you to integrate the behavior of the physical world with the behavior of software and networks. And the behavior of the physical world is going to be something you observe through sensors, and it's going to be something you control through actuators. And the properties of those sensors and actuators can strongly affect the behavior of the system. So this kind of modeling, where we're using differential equations to describe physical dynamics, is pretty useful for a certain class of physical systems. But in a cyber-physical context, we have a much richer variety of behaviors. We're not always talking about mechanical motion. We can be talking about a lot of other kinds of things, you know, packets coming in over the network that are going to affect the behavior of your system, things like that, which distinctly do not have the character of the physical dynamics of a mechanical object, and consequently are not particularly amenable to differential equation modeling, right? So we're going to talk about other kinds of modeling, and in fact today we're going to primarily focus on state machine modeling, which has a very different character from these differential equation models. And one of the interesting things that you find in the design of embedded systems and cyber-physical systems is that you almost always have to combine a multiplicity of modeling techniques. No single modeling technique actually will work for describing the entire system or work effectively. So you have to be able to combine these things. That's going to be a big emphasis in this course. We're going to look at quite a few of the models, the kinds of models that you can use. So the differential equations that we described are not particularly good for describing what digital circuits do or what computers do, because they talk about the dynamics of a system in a time continuum. And computers can't deal with a time continuum. They deal with discrete numbers, sequences of numbers, okay? So a step that you could take, a small step, towards being able to bridge that gap between the continuous physical dynamics and the world of software is simply discretize time. You could sample a signal, and the signal, your measurements of the physical world, your measurements of from the gyroscope, for example, become a sequence of numbers. That's a step in the direction towards software, but it's a rather small step, okay? And in particular, it's not very accurate for software controllers. Software controllers don't actually tend to behave in a discrete time way. I had a PhD student who worked up a rather clever sample problem. Actually, let me show you his image. And I just want to describe to you, a very simple scenario. So in the case, you remember when I talked about the controller that controls the position of the tail of the helicopter, I pointed out that if you get the polarity of the constant wrong, the system becomes unstable, right? Your correction is in the wrong direction. As the tail starts to rotate, you correct by increasing the rotation rather than by decreasing. That leads to an unstable system. Okay? Controllers can take systems that are intrinsically unstable. The helicopter is actually intrinsically unstable, and they stabilize it by using a feedback loop. So as long as we got the polarity right, the helicopter, which by itself as an open loop system without a controller is unstable. It will crash. Okay? With the controller, you can control the position of the tail. So you close the loop with a controller to stabilize the system. So this is a typical strategy in control systems. So this student of mine, Jie Liu, came up with a very simple scenario where he was using controllers very similar to this helicopter controller, but with a twist. He said, okay, let's assume that these controllers are implemented in software, and that the software is using a multitasking operating system, Linux, for example, and that it context switches between these controllers to share the same CPU to implement the control law, which is the application of the correction signal. And in his scenario, he came up with a context in which, by controlling the priorities of the two tasks that were running at the same time under this operating system, he could make one or the other system stable, but not both. Okay? So, but then he introduced a little twist. The twist is in a multitasking operating system, there's kind of two classes of scheduling policies that might be used. We're going to talk about these scheduling policies, by the way. Well, one of them is preemptive multitasking. So preemptive priority-driven multitasking says, if a high priority task is ready to execute, then stop whatever you're doing and start executing that high priority task. Okay, so you take whatever task you're currently working on, you suspend it, and you switch to the high priority task. When you're done with the high priority task, you go back to resume what you were doing before. Okay, that's called a preemptive priority-driven multitasking operating system. It's preemptive because when the high priority task becomes enabled, it will preempt the execution of the previously running task. So under a preemptive priority-driven system, he could stabilize one system but not the other. Whichever one had the higher priority, he could make stable, but the low priority task would become unstable. Okay? He then showed that if he changed the scheduling policy to non-preemptive, meaning simply that you don't interrupt a task, okay? If a high priority task becomes enabled, you complete what you were doing, finish that task, and then go to the high priority task. Okay? Under this non-preemptive policy, he could stabilize both controllers. No control theory can explain why this happens. Okay? It's in fact counterintuitive, because in control theory there's kind of a rule of thumb that if you reduce the overall delay in a feedback loop, systems tend to become stable. And the preemptive system reduces the overall delay in the control loop. The non-preemptive system, on average, actually increases the delay. And yet, with the non-preemptive system, he was able to stabilize these, and with the preemptive system, he was not able to stabilize them. the point here is that the behavior of the operating system affects the overall dynamics of the system in ways that can be extremely difficult to understand. Okay? I mean, it's already hard enough to understand control theory. If you've taken 128, you know, this simple proportional controller that we have, you can grok at an intuitive level because it's just measuring error and, you know, making a correction in the opposite direction of the error. But control systems get much more sophisticated than that, and they're pretty hard to understand, even when you idealize things using these differential equations. As soon as you introduce the behavior of an operating system, they become incomprehensible. Okay? And nobody has theory that deals with them. That's not quite true. I mean, there's actually a lot of the current work in control systems, research work, you know, PhD theses getting written at Caltech are about understanding how control systems behave when you have networks intervening, when you have operating systems intervening. But the progress is slow. It's a very difficult problem. Okay? Yet it's that problem that's at the heart of embedded system design, because you have to understand the joint dynamics of your physical plant and your software and your networks. Okay? So in practice, what happens is a lot of times the way that engineers design these systems is very ad hoc. They try things out, they measure them, they test them. If the helicopter crashes, they go back to the drawing board and try to figure out something else. Kind of sad. But the emphasis of this course is on what I believe to be an ongoing problem of finding better ways. Okay? So we're going to talk about what some of the steps that you can take. But I'm not going to pretend to you that I'm going to teach you how to solve all these problems. Nobody knows how to solve all these problems. This is an ongoing field. It's relatively immature. Okay? I'm going to try to give you enough background that you will be able to then understand improvements as they come along. But I'm not going to give you all the answers. I'm going to give you a lot more questions than answers. So this in particular is a problem that, you know, my PhD student posed this challenge problem about 10 years ago, and still nobody has a good explanation of why these things stabilize with a non-preemptive operating system and don't stabilize with a preemptive one. Okay? All right. So the key concepts here are that the models describe physical dynamics. We can use models as a specification for a system. So if I look at that helicopter controller, I can treat that as a specification, and then I can say, all right, now I want you as an engineer to go and build an implementation that does that. Okay? That's a useful role that models can play. They can serve as specifications for systems. In fact, in general, when models are being used as specifications, people use the term model-based design. Traditionally, in most systems out there, the specifications are text written in some language, usually written into a contract. Okay? A lawyer writes the specification saying, I want you to design a system that will do blah, blah, blah in words. Right? That's the traditional kind of specification. Those kinds of specifications are, of course, vulnerable to all of the problems that human language has, which is ambiguity, possibility for misinterpretation, incompleteness in the specification, etc. The principle of model-based design is to use models that have a distinct semantics. They have a mathematical meaning, and use those as a specification. No physical system will exactly match the behavior of those models, right? Why is that? I mean, so I have this differential equation that describes the rotation of the tail of the helicopter. Why can I simply assert that you cannot, as an engineer, design a helicopter that will match that model perfectly? Why? Yeah. That's right. I mean, the physical world is nasty, right? I mean, you know, my model might be based on a certain measure of the moment of inertia of the helicopter, right? What happens when ice forms on the tail of the helicopter and the mass changes? What happens when the temperature changes and the flexibility of the metals that make up the helicopter change? Our models can't include all the possibilities. And it's pointless to even try. right? You want to design systems against models that have a reasonably high fidelity, and then you want to make systems adaptable. So you want to put in sensors that say, what do you do if you detect that that control system is in fact not doing what the model says it should do? Then you would like to design a system that will react in some way. Okay? So you want to be able to design against models and then detect situations where your models are no longer being followed by your physical realization. I should point out that the languages that we use for describing models can themselves be modeled. Okay? People use the term meta-models for a model of a modeling language. So when we talk about describing the helicopter as these boxes where each box represents a function, where the domain is a set of functions and the range is a set of functions, I've just given you a meta-model. Okay? I've given you the semantics of a framework within which I construct models. Okay? That's a useful thing to do, particularly when you're using a plethora of distinct models. If you're using different models in the same design, it's useful to know which model you're talking about. If I write some expression for you or draw some picture, it's useful to know what the meta model is so that you can agree on what the interpretation of that picture is. Okay? All right. Let me switch to, how do I do that? Okay. So I'm gonna now start talking about the content of chapter 3 in the textbook, which is modeling modal behavior. Okay, modal behavior, unlike the helicopter design that I was talking about, the helicopter design is talking about continuous behavior, the dynamics of a system in a time continuum. Modal behavior is more about discrete changes in behavior. They occur at particular instants, such as, for example, the motor driving the tail rotor suddenly fails for some reason, right? That's a mode change that's going to change the dynamics of the system. So those kinds of modal behaviors are prevalent, and what we'd like to do as a first illustration of how you combine distinct modeling techniques is show you how you can take these models of the continuous dynamics and combine them with models of modal behavior. Okay? So an integrator is an example of one of these continuous models where I can draw it as a box. It's got an input x, where x is a function that maps the reals into the reals. So x is a member of the set of functions mapping the reals into the reals. This set can be written like this, okay, or like this. Actually, let me take a moment to explain this notation here for sets of functions, because I think it can lend some insight. Let me see if I can get this. Okay. And I apologize on the screencast for the lag that will inevitably occur here. But if I have a function that maps a domain A into a range B, I can write this f as a member of the set A to B. But this set is often also written as, whoops. It's the wonder of a multi-touch screen. I just hit the erase button with the heel of my hand. It is not the easiest to get used to a new technology like this, but okay. So, all right. So this can be written. This set of functions mapping A to B can be written as B to the A. Okay? Why? Why do mathematicians use that notation? Well, suppose I have a set B what does B squared mean? It's a set of two tuples of elements from B, right? So this is also written B times B, okay? It didn't show up on the screen. That's why they call it a not work. I appear to have lost the network connection to the... Yep. Well, what can I say? It's a not work. Okay, I'll use the whiteboard. Screencasting doesn't always do what we want, does it? Okay, so B squared is B cross B. All right, a particular member of that set, if I have a lowercase b, I'll often use this. By the way, don't count on me using lowercase for members of sets and uppercase for sets. In fact, it would be a really bad idea because we're often going to talk about sets of sets, in which case the member of the set is itself a set. So, but okay, so if lowercase b is a member of the set B, then lowercase b is a two-tuple, a pair of elements where B1 and B2 are both members of the set B. Okay? That's a standard notation. All right. Well, one way to think about B to the 2, okay, is that it is the set of all functions that map the set 1, 2 into B. Right? Because every element of this set has a value for index 1 and a value for index 2. Therefore, a member of this set can be interpreted as a function that given index 1 gives me value B1, and given index 2 gives me value B2. Okay? So von Neumann in the 40s or so introduced a mathematical concept called the von Neumann numbers, where he said, okay, let's define the number 0 to be the empty set. Okay, so the number 0 is the empty set. The number 1 is the set consisting of a single set, the empty set. Okay, the number 2 is the set consisting of the empty set and the number 1. Okay, and so on. So using these von Neumann numbers, von Neumann actually basically showed that set theory was sufficient to build number systems. Okay, so now 2 in fact is a set. Okay, and consequently this interpretation of b to the 2 as a set of functions that map this set into that set becomes perfectly natural. Okay, so here's a pop quiz. What is 2 to the b? Yeah.
It's a function in the domain B that maps.
That's right. So this is going to be the set of all functions that map B into either, I guess, yeah, this is, so the number 2 is the set, actually 0, 1, right? So this should be, my indexes should probably be starting at 0 to be consistent with the von Neumann numbers, right? Okay, so 2 to the b is the set of all functions that, given an element of b, tell me assign either a value 0 or a value 1. 2 to the b is interpreted as the set of all subsets of b. Okay, that's also called the power set. Why? Yeah. Yeah, actually, I can't. Oh, wait, maybe that'll work. Okay. Sorry. Can you guys see this? Okay. I guess the blackboard's not an ideal technology either, especially when there's obstacles in the way. Okay, so why can we interpret 2 to the b as being the set of all subsets of b?
Returns a 0 if it's not in the subset.
That's right. So given a function in this set, every element of b is associated with either a 0 or a 1. Okay? So I can interpret that as if it's associated with a 0, it's not in the set. If it's associated with a 1, it is in the set. The set of all functions, therefore, of this form gives me the set of all subsets of b. Okay? So as a consequence, that number system gives us this ability to interpret domains and ranges in this way and write, and that's the reason that mathematicians will tend to write a set of functions in this form, where it's easy to get confused, right? But the exponent is the domain, and the mantissa is the range. Okay, and if you forget that, you can reconstruct it by just thinking, well, okay, well, what is b to this b squared, right? Well, the 2 has to be the domain in order to get a 2 tuple. Okay. Now, suppose that I want to construct an infinite sequence of elements of b. An infinite sequence. Okay. How might I do that? I want a sequence. So what I'd like to be able to represent is something like a sequence of numbers b0, b1, b2, b3, etc. Yeah. So I could take, but keep in mind which is the domain and which is the range, right? For every element in the natural numbers, I get an element in B. Okay? Mathematicians, by the way, often write this set of natural numbers using the symbol omega. Okay? And that was actually a terminology introduced by von Neumann. So in the limit, these von Neumann numbers become omega, which is the set of all such sets. Okay? So as a consequence, you'll often see the notation b to the omega is the set of all infinite sequences. Of elements from B. Okay. What about B to the R? What's that? Yeah. Yeah. So that would be if for example, if B happened to be the real numbers, okay, then this is the set of all continuous time functions, right? Where the domain is the real numbers and the range is the real numbers. Okay? But in principle, you could define something with other sets B that are functions of the reals also. They don't need to be real numbers. Okay? All right, so that's notation, but yeah. So hopefully with that little introduction, if you see the notation A to the B when A and B are sets, it won't be confusing. All right, so let's look at a system that has more discrete behavior. So suppose that you're an embedded system designer and the owner of a whole string of parking garages comes to you and says, well, I'd like to put little displays outside the parking garage that tells me how many spaces are available. Okay? And the way you're going to do this is cheap, right? The guy doesn't want to instrument all the parking spaces, so you're just going to count the number of cars going in and out. Okay? So you only have to put sensors at the entrance and the exit of the parking garage. All right? So you've got some sensor that we might call an arrival detector, and another sensor that is a departure detector. And we have this subsystem that we call a counter that is going to keep track of how many cars are in the garage. Right? Now, what is this? What are the inputs to that counter? So part of what we have to do with modeling systems is we have to get precise quickly. Okay? It's not enough to just say the input to the counter, the up input to the counter tells you when cars arrive. That won't do. Okay? How does it tell you when cars arrive? Is it something that can occur at an arbitrary time? At any time it can tell you a car just arrived? Is it something that can only occur once per second? Okay? Is it something where it's, you know, packets coming in over the internet and there's some limit on the rate at which the packets can arrive? These things are important in the design of the system. Okay, so for this example, let's just assume that the function up, which is the input to the counter, is a function whose domain is the reals and whose range is is the set of two elements, absent or present. Okay. This kind of signal is commonly called a pure continuous time signal. Okay? So a pure continuous time signal is a member of the set absent and present raised to what power? The reals. Okay? For every member of the reals, it's either absent or present. Now, is this a good model of what a sensor of at the input of a parking garage is going to give you? What's the fidelity of this description of this sensor? How would you build a sensor that counts cars going into a parking garage? Yeah. Could you? Yeah, you could do something weight-based. You could put kind of a scale there. What other ideas? That's a nice one, right? Yeah, if you take a ticket, a car went in, right? That's actually nice because the sensor already is, you know, I mean, it probably needs to keep track of when you run out of tickets anyway, so the sensor's probably already there. That's a nice, simple one. Yeah? Another idea? Sorry? Change of capacitance. That would be another one, yeah. As long as people aren't driving plastic cars into your parking garage, you'd be okay. Yeah? A photo interrupter would be another one, yeah. You'd probably have to, you'd have to somehow do something to ensure that, you know, if a pedestrian comes and stands in the way of your photo detector for just the right amount of time and then moves on, you don't count that as a car. But that could be an interesting design challenge. But yeah, you could possibly do that. Any other ideas?
Image recognition off the camera.
Image recognition off the camera, yeah, that would be another possibility. That's a rather complicated solution. Very different from counting the tickets, sort of at the opposite extreme, probably. Any others? Yeah? A rangefinder that does what? Right, but what would the physics be? That's kind of, you know, and a sensor. Ultrasonic might work. Yeah, absolutely. You could measure that something is in front of you using sound reflections. Nobody's mentioned what is probably the most commonly used one, which is a magnetometer. Okay, this is simply you put a magnet in the roadway and you detect distortions in the magnetic field, and plastic cars mess that one up too. So, anyway, yeah, all of these are possibilities. But so let's assume it's the tickets. Okay, because I think that's the best idea I heard today. As long as you're handing out tickets, you might as well count them. Yeah, that's right. You could mess it up with passersby coming and taking tickets just for fun. You probably need the magnetometer to just dispense the ticket. I guess I don't know. Actually, I mean, there's a good issue here, right? Which is generally when you're designing embedded systems, you care a lot about security, right? What are people going to do to try to mess up your system, right? You've got to be paranoid. You've got to try to think through what are the adversaries. You think everyone out there is an adversary. They're trying to mess you up. They're trying to make sure no one buys your product because it messes up too often, right? How do you defend against them? This is a good thought exercise when you're designing embedded systems. Okay, let's assume that we're doing the ticket counter. Then is this model of up a good model? Maps the reals into absent or present. Yeah.
I mean, I suppose it has high fidelity, but it would also make
Yeah. So the comment is that the fidelity might be high, but it might lead to an impractical design that somehow, because we're dealing with real numbers here, if we want to actually record those times, for example, it might put a lot of complexity into the system. What else? Yeah, that's a good point. You might want to map this into a sequence of absent, present, absent, because what would it mean if your detector, say, if I plot the value of the detector versus time, so the horizontal axis is the real numbers, and the vertical axis has two possible values, present or absent. Okay? Suppose that my input looks like this. You're absent for a while, nothing's happening. Then it's present for a while, then it's absent for a while. How many cars arrived? Hopefully one, right? But how many times was this present? Well, actually an uncountably infinite number of times, right? So there's two interpretations there, right? Either an uncountably infinite number of cars arrived, or there, only one arrived, and hopefully it wasn't, there wasn't a tailgater that snuck in right after it, right? So there's problems of potential problems of interpretation here. Yeah. Sorry.
You should check that the calls to end or have to arrive.
Yeah. That's right. You could have someone that pulls in, grabs a ticket, and then backs out. Yeah. Yeah, so that's a good point. I mean, one way to fix this would be, if in fact you want to interpret this as a single arrival of a car, then you probably want to count up on the transition from low to high, and not on, every time this thing is present, you count a car. Okay. We can do a little bit better than that, and say that we're going to say that this signal is discrete. Okay? What does it mean for a continuous time signal to be discrete? right, let's get some intuition. First of all, if it's a discrete signal, do you think that plot of that I showed over here, this sketch that is present for a range of times, is that a discrete signal? No. So intuitively, if we assert that the signal is discrete, we could rule out that kind of signal. Okay? So intuitively, a discrete signal would be one where you have the horizontal axis being the reals, you have present and absent being the vertical axis, and at any particular time, you might get a present, okay? So if it's present here, absent everywhere else, okay? Present here, absent everywhere else. Present there, absent everywhere else, okay? Yeah? Oops, sorry. It's a good thing this isn't being screen captured. Right? It's terrible when your mistakes get recorded for posterity. Okay, so intuitively, in this discrete signal, these the present events are somehow isolated. Okay, they're there by themselves. There's nothing around them. This signal is in fact absent almost everywhere. Okay, this almost everywhere is actually a mathematical term. Okay, one consequence of it is, suppose I assign the value 1 to present and the value 0 to absent. What happens if I integrate this signal? What's the integral? Integral is 0. Exactly 0 everywhere, right? These events have no oomph. They've got no power. There's nothing there almost, right? You blink and you miss them, right? They're somehow isolated, okay? Now, what about, suppose I were to tell you, okay, let's take a signal that has this sort of character. It'll also integrate to 0. But the signal will be present for rational real numbers and absent for irrational real numbers, okay? So if I plot it, it'll look like this, right? It's in fact absent almost everywhere, okay? It's absent for irrational numbers, present for rational numbers. It integrates to 0. Is it discrete? We hope not. Right? Because if that signal is discrete, there's something that's not the kind of signal we want, right? We ought to find a way to rule out that kind of signal, okay? Because if we define discrete signals so that they can admit this kind of behavior, then we're going to be kind of stuck having to do designs that are capable of dealing with this kind of signal, and that's going to be hard, right? So we'd like to, in fact, rule out these kinds of signals. So we can do that. We can give a technical definition for discrete signals that rules out this kind of behavior. Okay? Yeah. We're still talking continuous time. The time axis is the real numbers. Okay? So time is a continuum. Okay? Events can be present at any time. Okay? So we want to rule out this kind of signal. So just being absent almost everywhere is not enough to be discrete. Okay? We also need, in addition to being absent almost everywhere, that the time at which events are present can be counted in order. Okay? Can be put into an ordered list of numbers. Okay? You can't do that with the signal that is present for rational numbers and absent for irrational numbers, right? Because between any two values that are present, there's an infinite number of other values that are also present, okay? So you can't construct such a list of times at which the events occur, all right? I'll refer you to the textbook for the formal definition of this, okay? But the intuition is simply that the events at which, the times at which the signal is present will occur in an ordered list, okay? And as long as I can put them in an ordered list, then I have a discrete signal. Now I can go a step further and I can say that the signal is sporadic. Okay? And a sporadic signal is a discrete signal that has an additional constraint, which is that there is a minimum time between events. Okay? So that means that these events cannot be arbitrarily closely spaced. So for example, suppose that I have a signal. Let's go over here. Suppose I have a continuous time signal that looks like this. It's present or absent as a function of the reals. Okay? So present, absent. And let's say this is 0, this is 1 along the horizontal axis. And what happens is I get an event at time 0, an event at time 1/2, an event at time 3/4, an event at time whatever that is, and so on. Okay, I keep dividing the interval in half. And I get an infinite number of these events before time 1. Okay? Is this signal discrete? Yes, right? Is it sporadic? No, not sporadic, right? So the sporadic constraint can rule out these kinds of signals. This kind of signal, by the way, is called a Zeno signal. Okay, why is it called a Zeno signal? Well, because this mythical Greek guy, actually he wasn't mythical, he was an actual Greek mathematician. He proved, in fact, that you could never get from point A to point B, because you would always go halfway, and then halfway again, and then halfway again, and then halfway again, and then halfway again, and so therefore you could never get from point A to point B. So as a consequence, this is called a Zeno signal. Now, let me give you a nastier version of this. Suppose that I have this in addition to these events. I also have an event at time 2. Is this signal discrete? No. Okay? The mere presence of that event at time 2 makes it not discrete, because I can no longer list the events in the order in which they occur in a list. That list will never include this event at time 2. Okay? So discreteness also rules out these kinds of signals. Sporadic gives us a more better behaved kind of signal. Yeah. Yeah, so in order to be discrete, I have to be able to give the times at which events are present in an ordered list. Okay? So I can start to construct such an ordered list. It has the number 0, the number 1/2, the number 3/4, the number, what is it? 7/8, thank you, and so on. Okay? When do I get to 2? Yeah, I mean, never, right? The list will be infinite, and I still haven't gotten to 2. Okay? So discreteness also rules out this kind of signal, but yeah, question.
You wouldn't be able to reach 1 either, right?
You wouldn't be able to reach 1 either, that's right. So,
1 is still not discrete.
That's right. So if there's an event at time 1, it's still not discrete. Yeah, exactly. Yeah. Yeah, the range is this set of two elements, present and absent. Okay? Range means the range of the function, or the codomain. These are, if the range is present or absent, we call the signal pure. Okay, a pure signal has no value at a time. It's just present or absent. Okay, that's what we mean by a pure signal. It's just present or absent. It doesn't have any numerical value. Okay? Okay, so now we've refined our model of this signal up. The signal up is, in fact, going to be a sporadic signal, where in practice we're going to, based on the physics of the system, say, well, there's got to be at least 10 microseconds between cars, no matter how fast they're coming in. Okay? Otherwise, something is really wrong with the universe. Okay? So, all right, so we can deal with this as a sporadic signal. Similarly, down is also going to be a sporadic signal, but notice that these two are completely unsynchronized. So one key element of this model is that unlike something where I was using sampled data, right, the up and the down signals can be arbitrarily interleaved with arbitrarily small time gaps between an up event and a down event, right? And that actually does reflect the physical world. You can have a car arriving and leaving at the same time, essentially, or within nanoseconds of one another, and your system had better be able to deal with that. Okay? If you design it this way. So, all right. So then the counter can be represented as a function in the form shown here. How do we interpret this domain of the counter function? Capital P is the set of input ports of this box, up and down, or equivalently, the set of input functions. Okay? It's got two elements, up and down. So the domain of the counter function is the set of all functions that map reals into absent or present. Okay? And then we're going to deal with a subset of sporadic signals in that set. Okay? Raised to the p. Why is it raised to the p? There's two inputs. For each input, I need such a function. Okay? So the counter box is a function whose domain is a p tuple of sporadic signals. Okay? Where p is simply the set of names of the input ports. I want to emphasize that this style of modeling is extremely powerful. Okay? You can describe systems that are very rich and complex in behavior using this style of modeling without constraining yourself to assigning numbers to everything. You can just give things names. Okay? It's a very powerful modeling technique. Okay, the codomain of the counter function is the set of all functions that map that map the real numbers into either absent or the natural numbers. Why that? So if I were to sketch this, okay, the output of the counter box is a function of the reals. At any given time, in fact, almost everywhere it's going to be absent. Absent almost everywhere. Okay? Where it's not absent, it's going to give me values in the set of natural numbers. Okay? So when the first car arrives, after opening the garage, I get an event that tells me there's one car in the garage. That car finds that the garage smells bad because it's just been painted, so he leaves, and we go back to 0. Okay? And then people have to start arriving, so we get car arriving, another car arriving, a third car arriving, a car departing, then another car arriving, and so on. Like that, right? So the way that I've modeled this system, yeah, question?
Sorry, why is it that these ones aren't?
Very good question. Why? I mean, I could have modeled this system quite differently, where I took the codomain to be the natural numbers without absent, okay? And I simply start at 0. When a car arrives, I bump up to 1, and I stay there until the car leaves, and then I go back to 0, and so on, okay? I could have done that, but I didn't, okay? Instead, I'm describing a system that's much more discrete in the sense that my display is not going to be getting a continuum of data from me. It's only going to get data from me when the count changes, right? So that's different. You know, there's two different designs, but you would build these things differently, right? The display might be connected over the network somewhere, and what I want to do is send it, you know, send a packet over the internet to this display, in which case this model here is a better model, higher fidelity for what actually happens. If the display is immediately connected to the box and I just have an electrical signal that is driving the display, then this might be a better model. Okay? Both would be valid models, but I'm going to assume we're using this model here. Now, I'm going to assume the inputs are sporadic. Yeah, both inputs are sporadic. So in and up are sporadic signals. Okay, first question. Is the output discrete? This is not a trivial question, okay? The answer is yes, right? But let me emphasize to you why it's not a trivial question. First, is the output discrete? Is the output sporadic? So sporadic means that there's a minimum time, that's a fixed property of the signal, between events. Yeah.
Theoretically, you can't say that.
Right. Theoretically, with this model, assuming that my counter instantaneously tells me when things have gone up or down, then the output will in fact not be sporadic. Okay? Suppose that the inputs are not constrained to be sporadic. They're only constrained to be discrete. Then is the output discrete? No. Right? Why not? Well, because one of them could give you a Zeno signal, and the other one could give you a, just something with regularly interspersed events, and we'll end up with this scenario that I described before, where I have this Zeno signal and other events after it. Okay? So if the inputs are only constrained to be discrete, the output cannot be assumed to be discrete. If the inputs are constrained to be sporadic, the output is discrete, but not necessarily sporadic. Okay? Pretty subtle. How does that translate into practical design? Well, I mean, if you were to design this thing as a simple circuit, right, you might, in fact, have near simultaneous arrivals and departures of cars. And your downstream system, the display, is going to have to be able to deal with that. If it can't deal with it, it's going to give incorrect displays. Yeah? Why is the output not sporadic? Because the input, think about, basically the value of the count goes up every time a car arrives and down every time a car leaves. But I could have a car leave arbitrarily close to the arrival of a car. So the time between these two events, there's no lower bound on that time. The inputs are sporadic. So there's a lower bound on the rate, on the time between cars departing. Okay? But the previous departure occurred way back there. Right. You see it? Okay. Does everybody see it? If the inputs are sporadic, the output is not necessarily sporadic, but it will be discrete. Okay? If the inputs are only discrete and not necessarily sporadic, then the output is not necessarily discrete. Okay? These subtleties matter because they actually have implications in design, right? You can get, failures in design where, the counter gets an up count and a down count too quickly and it fails to record one of them. Okay? So you want to be able to characterize these systems more carefully. Okay. So, yes.
We have one interest for both arrival and departure.
That's right. If we had just a single input representing both arrival and departure, and we could somehow assert that that input was sporadic, then this problem would go away, right? Then the output would be sporadic as well. In fact, in general, the subtleties in system design rarely occur when you have inputs, you have boxes with only a single input and a single output. The subtleties occur when you have multiple sources of stimulus being combined. Okay? Yeah.
So you wrote over there that it's absent almost everywhere.
Right.
So does that mean that whenever the system's not receiving input,
That's right.
so would that affect our evaluation? We have infinite absent ones in each of them.
That's right. So this is an important point. What we mean by sporadic is that, there's an uncountably infinite number of absents between every two non-absent signals. Okay? And that doesn't interfere with sporadic. Absent is treated kind of specially. It's allowed to occur at very high rates. Nothing can happen very fast. And it can keep happening. Nothing can keep happening. Right? That's what we mean by, having it be absent almost everywhere. Okay. Someone recently talked about, designing systems that do nothing well. Right? A system that deals with long intervals of absent is a system that does nothing well. Okay. All right. So the way that this system is actually going to behave, of course, is, the box that is doing the counting here, we can assume that it's just operating continually, looking at its inputs, and they're absent most of the time, so it's sitting there scratching its head, just being really bored, and then suddenly something happened, I'll count. But that would be kind of probably not a good way to design that system, right? And maybe not such a good way to think about its behavior. What you'd really like is a system that just sort of wakes up when a car arrives, right, and does something, and then goes back to sleep and doesn't consume power or anything, just sits there quiescent when there aren't any cars, right? So when we have a system that is discrete, we can describe its behavior as a sequence of reactions, where the reactions themselves are discrete. So every time either a car arrives or a car leaves, this counter will react by either counting up or counting down. So that reaction produces a change of state in the system, okay? And then after the reaction, it just goes back to sleep again. So the abstraction here is that the behavior of the system is represented as a sequence of discrete reactions. And at each reaction, it does a count, okay? At each reaction, the input ports have some value. One might be absent, one might be present. They might both be present. They might both be absent, but that would be kind of an uninteresting reaction. Okay, so generally, the reactions are going to occur only when at least one input is present. And we talk about evaluation at the time at which the reaction occurs as simply being what are the values of the input. So when a reaction occurs, there will either be a car arriving or a car departing, or both. Okay? By the way, the or both is one of the things that is the sort of thing that gets constantly missed when your specifications are written in text rather than in models, right? You're right. If I wrote a contract with you that says you're going to build me a garage counter that in each reaction, either a car will be arriving or a car will be departing. If it's arriving, you count up. If it's departing, you count down. Period. Sign the contract, deliver the product. If a car arrives and leaves at the same time, you count up. And so you have an accumulating error. Have you met the terms of the contract? Yeah. Okay.
How would be the exact the same time?
Sorry?
How would you make this error with the exact the same time?
Well, the point is that the contract didn't say what you should do if there was a car arriving and leaving at the same time, and therefore you're free to do whatever you want and still be compliant with the contract. Right? It's really easy to miss those kinds of things when you're writing the specifications in text. It's a lot harder to miss those kinds of things when you're building a model. Okay? It's not impossible to miss them, by the way, but it's harder. Okay, so assume that the counter will only count up to the number of spaces in the garage. Okay? If a car arrives when there are no more spaces, it doesn't keep counting up. Okay? That could be a problem, by the way, but because there will be a departure when that car didn't find a parking space, and now all of a sudden it'll record that there's the parking space been freed. Okay, so you could get a defective design by having the state space be like this, right? This is probably only a valid state space if you assume that it's not going to let cars in when it's full, right? So these are the things that models expose, these kinds of subtleties, right? So here is a description of this garage counter as a finite state machine. It's got m plus 1 possible states, representing either there are no cars in the garage, there's 1 car in the garage, there's 2 in the garage, there's up to m cars in the garage. And when a reaction occurs, it can transition between states. So it could move from 0 to 1 if a certain condition is satisfied. And that condition is given as a guard on this transition between states. Okay? This guard is this expression right here. Up with a caret. This symbol means not down. Okay? So if you get if upon an arrival, upon a reaction of this state machine, a car is arriving and a car is not departing, then you transition from 0 to 1. Notice that the model is explicit about what happens if a car is arriving and departing at the same time. If a car is arriving and departing at the same time in this reaction, how does this state machine behave? It just stays in state 0. That's called stuttering, by the way. When you stay in the same state, you make no progress. That's stuttering. Okay? Make no progress. Okay? So this diagram represents the finite set of possible states and how you make transitions between them. The guards are expressions that represent, what are the conditions under which you make transitions. So I'm going to stop here. Next time, what I'm going to do is, I've actually given you most of the depth of the state machine models, but we're going to go over a little bit of the notation a little bit more so that we can describe more elaborate state machines, and we'll do that on Thursday. Thanks.